Hi, I'm Asada from the Technion, Israel Institute of Technology. CloudCT is a spaceborne mission of 3D scattering computed tomography, funded by the ERC. I'm going to tell you today a bit about a study we made to determine the most suitable payload concept for the mission. In this study, we considered setups of visible, shortwave infrared, and polarized imagers. First, a few words about our mission. CloudCT plans a formation of 10 cooperating nanosatellites. They will image cloud fields simultaneously from multiple directions at about 20-meter resolution. The images will be used in 3D scattering tomography, leading to retrieval of microphysical properties of clouds. At the moment, we focus on retrieving the liquid water content and the effective radius. In this talk, I will lay out a bit of the process we went through in narrowing down the payload concept, starting with defining what imager types to consider, what are the imager considerations, and finally, what seems to be the best overall possibility. Let's start with the imagers. We consider three types of imagers. Our model, Vadim, is demonstrating for you the features of each imager. On the left, you see Vadim in unpolarized visible color. On the right, you see Vadim in shortwave infrared. You can see his eyes are dark because of water absorption. This is actually the motivation in using SWIR. In the Nakajima-King method, Viz and SWIR are used together. Through absorption, SWIR is sensitive to the effective radius of the cloud droplets. Water droplets do not absorb much visible light. Visible light, however, is sensitive to the optical depth of clouds. The center images are Vadim's Stokes vector components. They're the output of a polarized visible imager, which uses Sony's polarized sensor. In this sensor, each pixel has a wire grid linear polarizer. Adjacent pixels have different wire grid angles, which are used to estimate the Stokes vector per 2x2 pixel block. In clouds, polarization is due to scattering. This is an image of clouds from Polder. When looking through a polarizing filter, you can see that there are scattering angles in which the degree of polarization is high. This angle range is the cloud bow and is strongly dependent on the effective radius if the droplet size variance is not too high. This is part of the motivation for considering polarized imagers. In the simulation, it looks like this. You can see here a few satellite views. In the red box is a satellite view which coincides with the cloud bow peak, and you can see the high degree of polarization. Now let's talk about the imager considerations for our mission. Well, there are quite a few. I won't address them all here, but you're always welcome to contact us for a longer chat. One of the basic underlying considerations is the volume constraint. We're going to use nanosatellites in CubeSat 3U format, meaning an overall volume of 3 liters. The camera payload is restricted to a volume of less than 1 liter. This, of course, affects many aspects of the design. For instance, signal-to-noise ratio should be at least 100. SWIR sensors are more sensitive to dark noise than the silicon-based sensors in the Viz and Pulse imagers. So, they need onboard cooling, which takes up more platform resources like volume, power, and heat management. Considering calibration, the volume restricts us to vicarious methods. In this aspect, pole imagers cause additional complexity, since beyond basic calibration, they also need polarimetric calibration. This affects also resolution considerations. We require high spatial resolution for analysis of small clouds. The preference ground sampling distance, or GSD, is 20 meter at nadir. However, diffraction effects limit the resolution. Narrowing the point spread function at long wavelengths requires larger optics, which challenges our volume constraint. So for our SWIR payload, we had to settle for GSD of 50 meters. Now to some considerations for choosing a waveband. The basic considerations are signal contrast and intensity. Let's start with the visible spectrum. Our optical signal has two components. One is light scattered from the object, in our case the cloud. This is a desired component. The second is air light, which is light scattered by air molecules and aerosols. This is undesired because it induces photon noise on top of the signal coming from the cloud. Atmospheric correction cannot undo photon noise. This is true also for the polarized signals. These are simulated images of a cloud at different wavelengths. The top are simulated without molecular scattering. The bottom plots have air light. See how the air light reduces the contrast of the cloud, and how this effect increases at shorter wavelengths. On the other hand, the intensity of the solar spectrum decreases in longer wavelengths. We are also limited by the quantum efficiency of typical sensors, which also decreases in longer wavelengths. In our current simulations, as a midway between these effects, we use the red channel between 620 and 670 nanometers. In SWIR, from similar considerations of signal intensity and quantum efficiency constraints, our waveband is around 1.6 micron, which is also used in the MODIS instrument. Now, to the final line of our considerations, that we give the most weight to, the suitability of the imager and its susceptibility to uncertainty. This helps us focus our final question. What is the best overall possibility? To answer this, we give priority to the considerations of retrieval quality and stability to uncertainties. In order to quantify these, we ran simulations modeling each imager according to its typical specifications. In order to quantify stability, we introduced uncertainties to the calibrations. We considered two effects, stray light and random gain uncertainty per pixel. We considered 4 cases of imager setups. Option 1, 10 views with visible cameras at 20 meter nadir resolution. Option 2, 8 views with visible cameras at 20 meter nadir resolution and 2 views with SWIR cameras having nadir resolution of 50 meters. From technical reasons, we can't use both imagers on the same platform. We use the SWIR close to nadir to avoid losing resolution. Option 3, 10 views with polarized cameras in the visible spectrum at 20 meter nadir resolution. And option 4, 10 views with visible polarized cameras, but through orbital motion, one satellite will sample 8 additional views in the cloud bow angular range in up to 30 seconds. These are the clouds we used as ground truth. They're created by large eddy simulation. The color bar indicates the liquid water content. The mean effective radius values reach up to 10 microns, and the optical depths are between 19 and 72. The retrieval quality is compared without sensor uncertainties other than noise. These values are mean relative errors of the cloud set. The pole setup has a significant advantage over both VIS and the combined VIS and SWIR setups. You can see the cloud bow scan gives a slight additional advantage to the polarized setup. For these retrievals, we had only radiometric noise. Now, let's add uncertainty. Stray light is an artifact of optics, a result of inner reflectance. This is an example of a ghost image caused by stray light. Out of the overall field of view, the pixels comprising a single cloud cell are relatively few. So, in the pixels we use for tomography of a single cloud, stray light is considered spatially uniform. For each imager in the setup, we consider stray light of a different random value. The stray light is randomly sampled from a uniform distribution defined between 0% and 5% of the mean intensity of the image. This is the difference in the relative error caused by stray light, meaning the new relative error, which takes into account uncertainties, minus the old relative error, which had only radiometric noise. I'm showing you here the difference per cloud retrieval. The different colors are different clouds. The difference in relative error is no more than 0.05 for all the retrievals. The pole setup is most stable. This is even more explicit when looking at the effective radius retrieval. The gain uncertainty is defined per pixel. The relative change in gain is randomly sampled from a normal distribution with standard deviation of 5%. For the polarized imagers, random gain uncertainty is applied per sensor pixel prior to the Stokes vector calculation. The consequence of gain uncertainty is more significant than that of stray light. However, the pole setup is relatively stable, especially in the retrieval of the effective radius. This finding is significant and also non-trivial. In pole imagers, as I already mentioned, Stokes vector components are calculated by relying on 4 radiance values. Here, each of these values has a different random gain uncertainty. While in Viz and SWIR imagers, each pixel is affected individually, in pole, the Stokes vectors are affected by a combined uncertainty. Nevertheless, the pole setup seems numerically to yield retrievals that are more robust than in the other setups. To conclude, we presented an overall glance at the process of payload choice for CloudCT. We examined 3 types of imagers, each with its own motivation. We had many considerations and constraints to take into account, some of which automatically marked advantages and disadvantages for the different imagers. And finally, giving priority to considerations of retrieval quality and stability to uncertainties, we conclude that the pole setup appears to be most suitable within the mission constraints. Thanks for your attention. For more information about CloudCT and articles from the group, please visit our website. See ya!